Good morning. My name is John Weaver. I'm from the University of Illinois in the United States. My departments are materials science and physics, and today the topic is an overview of nanoscience and technology. This is a particularly relevant topic these days because countries around the world are investing in what are perceived to be particular opportunities for advancement in science and engineering. Now, if we think about what nanoscience is, if you have a group of 10 people gathering around trying to define the topic, you'll have 10 different perspectives. What was done in 2000, the year 2000, was that the American National Science Foundation and other organizations put together a national technology initiative. And in that, they had people who were biologists, physicists, chemists, material scientists, people from a wide variety of areas who sat together and defined what the topic was. And if we look at the transparency or at the slide, you'll see that it's a combination of topics which fit everyone. So everybody is a little bit happy and everyone buys into this topic. What is important is that this is materials, it deals with materials or systems of materials which have structures and components that are novel, to have specifically improved physical, chemical, or biological properties. That is, if I have something that's a centimeter cubed and I simply reduce it to a smaller size, but it has the same properties as the larger size, that doesn't count. It has to have something that's new and novel that lets me take advantage of those special properties in new technologies. So these would be physical, chemical, and biological properties, phenomena, and processes that are related to their size. And that seems to be a definition which has been accepted around the world. Now, if we define what nanotechnology is, whether it's science or science fiction, you can find both. But today I'm going to talk about the science and leave out the science fiction. What we think of as nanoscience, it is the understanding of atomic scale processes. That is, it's understanding, not necessarily manipulation. It is the understanding of processes at the atomic scale, because the atomic scale defines the size of an atom, and about 3 or 4 atoms in a row would be a nanometer, and that's the length scale that we think of. So if we think of a cubic nanometer, we're thinking about 3 by 3 by 3, roughly 30 atoms making up my particular system. So that's the small, and I'll go a little bit larger than that. Nanoscience, it is a technology. It's an enabling technology, not an industry. An industry, I would say, would be the automobile industry. It is not going to replace the automobile industry. Instead, the automobile industry will use nanoscience and nanotechnology, and already does, in making their products. An example, an analogy, would be understanding the flow of electrons in an applied electric field. Those problems were faced by the scientific community a century ago, and we learned to understand how to manipulate charge. From that understanding, we could then make resistors, and then transistors, and then devices, and then the internet, and then digital cameras, and everything that we have around us. That is, it's an understanding of a process that gets used in a wide variety of different applications. That's what nanoscience is going to be. Now, if we think about what the potential is, we say that there should be an enormous potential. Now, if you ask me where specifically we're going to have breakthroughs, that's more difficult. But I think that scientists from a large number of fields see within their field breakthroughs. For example, in medicine, what you'd like to do is have drug delivery. You'd like to avoid taking it through the stomach because that's a complicated chemical process that you'd like to get away from. You'd like to be able to inject it. You'd like to be able to have a medication which over time senses the need of the body to have a particular jolt of chemistry from the drug applied. That is possible, should be possible through nanotechnology. There are companies around the world, pharmaceutical companies, that are focusing on those kinds of things. We can expect breakthroughs. One hopes that 20 years from now, we'll look back upon medicine as it's practiced today and say that these were the dark ages, and that the 20-year from now future of medicine is quite different. But of course, those are promises, and we cannot guarantee those things. Now, if you ask when nanoscience emerged, you can think about nanoscience processes that have been used for centuries. For example, if you look at this image, you can see a very attractive cup that was developed, the Lycurgus cup, in the 4th century in Rome. And what it shows is that depending upon the angle of incidence of the light, the color changes. So it's green or it's red, and that's a process called opalescence, which now we understand is related to the fact that there are gold particles in that cup. I am quite sure that the Romans did not know what gold nanoparticles were, but they did know how to take advantage of a technology and make attractive artwork. The same would be true of the Chinese. About 1,000 years ago, they used gold particles in porcelain. Coloring was important. Gold nanoparticles, though they didn't know what they were, gave them the particular properties that they wished. A century ago, we developed ways to improve the wear of automobile tires by putting carbon black in them. At that point, we had discovered with periodic table, and we know more about the chemistry than the Romans did, but I'm not sure that we knew all the details of the carbon black and its processes. So all of these things which we can look back on and say are nanoscience, I would not include as my definition, the current definition of what is nanoscience. I require that we understand the processes. These people did not have the chemical periodic table, so they couldn't have understood it. Often the identification of the starting point or the vision for nanoscience and technology is traced to Feynman and a lecture that he gave in 1959 to the American Physical Society. And he said, and let me quote, "I am not afraid to consider the final question as to whether ultimately," so he has no timeline, but a long time in the future, "in the great future, we can arrange the atoms the way we want them, one by one, the very atoms, which are the constituents of matter, the way we want them, all the way down to the size where there are 2 or 3 or 10 put together." Then he says, what would happen if we could do that? What kinds of breakthroughs would there be if that were possible? And when can we possibly do it? Well, that was 1959. So if we add 22 years, we're in 1981. In 1981, Binnig and Rohrer, who immediately got the Nobel Prize for the breakthrough that they had, developed a scanning tunneling microscope. And a scanning tunneling microscope lets you see corrugation of atoms, not my knuckles, but atoms on a surface. You could see the atoms. So not many years after Feynman, you had a technique, an instrument that was developed that allowed you to see atoms on surfaces. That wasn't manipulating them yet, but it was seeing them. And then in 1989, 8 years later, Don Eigler and his group showed that you could manipulate them. And so if you look at this image that shows 35 xenon atoms on a surface, spelling out the letters I, B, M, and of course he worked for IBM at the time. One will never make products out of writing IBM at low temperature with xenon atoms, but the discipline that you would adapt in doing that can then carry forward into other processes which will, we believe, have applications. Now, the expansion of nanotechnology, or what have been the driving forces for nanotechnology, have been many. One has been, for example, the electronics industry. We've all heard about the Moore's law and the increase in speed and reduction in size for devices with time. That has been one size. We want faster, we want better, we want different kinds of devices. I would also say that there have been discoveries made over the years, as is always the case in science, so that we can build on the previous generation of work. And the particularly important advances, I would say, are those related to surface science. Because if I understand surfaces, then I can think about modification and manipulation of atoms on surfaces. We've had the development of theory, so that we now can predict the properties of matter without having to do the experiment. We can design things and then go into the laboratory and try to make them. In the 90s, there was the breakthrough that gave rise to studies of carbon structures called fullerenes, C60 and higher structures, and then carbon nanotubes, and then there was the work on self-assembled monolayers. All of those breakthroughs combined set the stage for something that we call now nanoscience and technology, but which of course goes back earlier in time. As we are now, and as we have been for the last half dozen or so years, we believe that in the next century, the physical sciences will marry the biological sciences. That is, there will be a merger as the physical sciences are able to provide new insights, the mathematical skills that we have, and the biological sciences are able to tell us what the important issues are. And together, we're going to have a great new future. And I think that's certainly going to be true. And it's going to be reflected in nanomedicine, nanotechnology, disease detection, and therapy. There's always the question of, are we using nanotechnology? Where, if I get up in the morning, will I find nanotechnology? Well, a very simple application, or not so simple application, but one that's common, is right here in a laser pointer. And the image that you see behind me is showing how a laser pointer works. There are a series of atoms buried in the center of a device that have a particular crystal structure and chemical makeup that are different, chemical makeup that's different from those around them, so that if I inject an electron and a hole, they will go to that very small object in the center, combine, and give off a photon. So I have a laser, which is very much nanotechnology. There is an interesting website by the Department of Energy which shows length scales. And it says on one side, this is man-made, and this is natural. And we start off at the large size, where of course we have ants, and we can say that they're millimeter in size, and something that we can make the head of a pin, which would correspond to the man-made side. And we can work all the way down, and as we work down, we can identify the length of the photon energy that corresponds to that dimension. And the image that I show here, relative length scale, provides a collection of different examples of what are man-made and what are natural. Things that are natural spherical objects would be the fly ash that comes from a coal burning furnace, where in the combustion process you burn the coal, but there are other impurities that are not burned. Aluminum oxide, which forms a spherical structure because it's at a high temperature as it goes up the smokestack. That would be a natural. Correspondingly, on the other side, you could have a microelectromechanical device that we can make that would give particular sizes. This image shows at the very smallest size the DNA, where the coil length is a nanometer approximately, and on the other side, something that I'll show again later, that is an assembled structure of atoms on a surface. So we can deal with all these lengths, and we're making progress at manipulating structure. It's an example of the challenge that's identified, and this, for example, this particular example says, let's develop a way of harvesting light. So let's have something which is photosynthetic, capture the photon, convert it into energy, and store it in an inorganic material. So this is the combination of a molecular structure, a complex molecular structure, combining with something which stores the energy, and that can be used in the future. We don't know how to do that, but that's something which is the challenge. A point of nanoscience is one that identifies how many atoms of a particular structure are the surface and how many are in the bulk. If I have one atom, it's clearly all surface. If I have one surrounded by 6, 3 and 3 in the top, I have 13, but 12 of those are the surface. If I go then to the next level, I can continue expanding this structure to the point where, for example, and this image shows that if I have 12 as a shell, then I'll have approximately 5,000 atoms, but 12,000 of them are going to be on the surface. So a significant fraction of anything that we make at the nanoscale is surface. So I must understand surface science, and I must be able to protect these structures, because if I make something like this that's this small and I expose it to the environment and it reacts, then it's no longer what I made, and I have to develop ways to protect that. So the grand challenges in what we're doing are synthesis, how to make these things, ways to do it, size selection, because if we say that the properties are related to the size, I need to be able to choose the size so that I can make the device that I want. I need to stabilize, that is to get away from those surface problems. I need to characterize. I need to come up with new ways to look at the process. Scanning tunneling microscopy is an example of a way to characterize these processes. And then if I make something that's really neat and has fascinating properties, I've got to be able to somehow build that into a larger structure. If it exists in vacuum, that's not particularly useful. It has to somehow be connected to other things that have wires that go out to the outside world. I'll come back to this issue of communication with the public because it's one that's very important, and one that scientists often do not do adequately. And with nanoscience as a new technology, there will naturally be people who are afraid of it, and we have to make sure that they understand what nanoscience really is. Now let's work our way through nanoscience and technology. I want to start by growing a thin film. Thin film will be a nanometer in one dimension. It'll be made up of atoms. I want to have the discipline to think about those atoms. So let's start off with a clean surface and a source of atoms. What will happen? If I have this in a vacuum system and I evaporate atoms from the source, they will arrive at the surface. Some of them will stick, depending upon whether it's a reactive site. Some of them will bounce off. And I can characterize those processes. If I do that and think about that surface in a little bit more detail, that is, I make a ball and stick model, then I can imagine what a surface really looks like. A surface could have flat areas, it could have steps, it could have a kink. An atom arriving on the terrace can diffuse. It can come to the step. If it comes to the step from the lower side, it can get stuck. If it goes to the kink, and then that's the best place to bond, then I'll have this top layer growing over the bottom layer. In addition, I can have atoms on the surface that will find each other, and they'll form clusters. And those clusters can be stable after a particular size, or if I give them temperature, I can have big clusters and little clusters, and thermodynamically, the big clusters will eat the little clusters, so they will grow. In addition, I can have three-dimensional structures, depending upon the details of the energies associated with a surface, the film of the cluster, and the interface. And the idea there is just like water beating up on your car. Depending upon the details, I'll get layer by layer, or layer with a blob, or blobs. And these images show, in a very simple cartoon, the processes associated with it. First, I have a planar structure. I can grow another layer on top of it, and that layer continues to grow layer by layer, and that's what I'll do if I'm making semiconductor devices for lasers. That's the structure that I want. On the other hand, I could have a wetting layer followed by blobs. Or I could have, as the third one shows, a simple conversion. Let's see, I've gone ahead. The center one was blobs. The third one is the layer followed by blobs. The fourth one is the one which is most likely to be the case. That is, chemistry occurs, reactions occur. And that means that atoms that I've added and atoms of the substrate have mixed to form a new compound. These are the only four possibilities that I can deal with for thermodynamic structures. This image shows examples of three of them. The one on the left shows gold atoms that have been deposited on a surface which are not reactive, and so they'll form three-dimensional structures, or what I call blobs. The one in the center shows germanium growth on silicon, where the first layer wets it, and then for reasons of strain, subsequent layers grow as blobs, huts. And the third one is layer by layer, where this particular set of images shows an indium arsenide and an indium gallium arsenide superstructure, heterostructure. Now there's some other things that are important which are not part of the equilibrium, which give me kinetically constrained features. And one would be a barrier associated with an atom coming up to a step and jumping over. If there is a barrier, and this cartoon indicates that, developed by a colleague of mine named Gert Ehrlich some 40 years ago, if there's a barrier that keeps you from jumping over, then you're going to accumulate on the top of the island. So if I have two islands, and I deposit, and everything that arrives on the island stays on the island until it forms another layer, and then another, what I'll end up with is this so-called wedding cake structure, which shows many, 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 many layers, and then areas in between where there's nothing. Now,